a second, wait a second, wait a second. Yeah. Так, I'm here and do so. Yeah. Yeah. Where's the save? Where is my... 1 second, I will get my... Something may happen, someone may get ill, so on. It's better to have recording. Okay, I want this. One of the problem. Okay, I can left this and that and I can leave. Okay, I left this. Time to start. Time to do something. Yeah. What I have for today? Switch this TV on. What I have for today? At first, I have a small example here. Example. I have a source of signal, small capacitor, 1/3 of nanofarad, and a circuit, coil 4.4 millihenry, and capacitor of 15 nanofarads. This is Earth, and this is first signal, the yellow line, and here I took the blue line or second signal. Yellow signal. What's with my camera? Easy circuit, isn't it? This signal is too simple. Let's add something. Let's, for example, add 1. I would like to add 1/3 of the I will add 1/3 of the third harmonic and 1/5 like this. Oh, something familiar. Yellow is a signal at the input, blue is a signal at the output, and red one is a Fourier transform result of the yellow line. The red one is the result of Fourier transform of this. What do we know about the signal? It's approximation of rectangular signal. 100% of the first harmonic, 1/3 or 50% of the third, and 1/5 of the fifth harmonic. Now I'll change the frequency. I want to change something like this. Good. And this one. This one should be better. Now, what we are observing? Maybe Google can answer. What we are seeing now? We have yellow line at the input, approximation of rectangular signal. Yeah? Yeah. And we have nice sign at the output. Yeah? Looks like nice harmonic signal, pure. Can you explain why we are sending in rectangular signal and getting sign at the output? Maybe Siri or Google can answer. Very simple network. So why? I'm sending rectangular signal and I'm getting nice harmonic at result. No capacitance is fixed. Here is my network. It's a fixed capacitance and nice fixed coil. 2016. I have signed my network. So, what's going on? Do you have any ideas? So, Google won't answer. What can we say about this network? Have we saw something like this previously? Last time we speak about such network, and I have shown and I have spoke about its characteristic as a function of frequency. Yes? Something like this. And the central point at a frequency omega 0 equals, I can say that omega 0 can be defined as 1 against square root of LC. By simple writing, if this is point A, imaginary part of A point conductance should become 0. This will yield me an omega 0, a resonance frequency. What is resonance frequency for this network? $15 nanofarads, 4.4 millihenry. Something like 19 kilohertz, isn't it? So, what's going on now? My signal has a spectrum of 3 lines. For A divided by P, 100%. This line, this red line corresponds to frequency of 19 kilohertz. Yes? Kilohertz. Corresponds to 3 frequencies, and this one will be 5 omegas. It will be 20%. 100% line and equals to 19 kilohertz. Now it's clear what's going on. From the set of 3 frequencies, this signal contains 3 different frequencies. This network acts as a band pass filter. From the all possible frequencies, what is done? It rejects all except its pass band. In my case, it separates first harmonic. And separated first harmonic is ideal sign. Okay, let's change frequency. Just and something like this. What's going on now? Input signal has a frequency approximately 6.4 kilohertz. See? Output ideal sign with a frequency of 19 kilohertz. How can we explain? How can we explain? Do you have any idea? Again, my signal contains 3 frequencies, 1 to 3, 3 spectral lines. Yeah? Again. Well, 100%, 33%, 20%. This one 6 kilohertz. Triple. Pass frequency of my network is 19 kilohertz, which corresponds to triple frequency. At this moment, that's what we see. So, appears what my network separates this line, this frequency. Can we check it? Look, I can the first. Did the signal disappear? No. I can switch off the fifth. Did signal disappear? No. But if I switch the third one, you see, signal disappeared. So, selected network from all possible frequencies separated only one, the frequency of the third harmonic. Yes? That's how bandpass filter works. We should see the same effect where? 5 times. Let's check. Now I adjust. Input rectangular at a frequency of 3.8 kilohertz and output harmonic. Actually, we see this line. Now we have something like this, where 19 kilohertz zero frequency corresponds to the third line of the spectrum. That's how selective network works. From the whole range of frequencies, it separates according to its characteristics. I'm shifting. In theory, I should shift the window of the network selected. But I have fixed window. This characteristic remains. I'm shifting all spectrum. It is not. In my case, it is not no principle to shift train relative to station or shift station relative to train. I'm shifting station. Okay, it was simple demo. As we saw, this network, and all network like this, are described with differential equation, and this differential equation has two roots. They are conjugated, meaning what we have an oscillation with one frequency, or they are real, meaning what we have a periodic decay. But we can go further. This still in, let's say, in circus theory. I can bring another network here. Network. I have this nice box. It reads Mursell inductance. 10 millihenries. Let's try to see what happens coupled by mutual inductance. Do you know what is mutual inductance? No? Mutual inductance. This one also goes to ground, and here I will add resistance as first example. So, what is mutual inductance? Maybe Google can answer. What is mutual inductance? Depend? Closer. Closer, but can be better. So, what is mutual inductance? Maybe you can answer what is a self-inductance. Self and mutual. My air ministry capacitor works on you. Key. When two or more coils share the same magnetic flux, it is mutual inductance. They are coupled by common or shared magnetic flux. One second, I will assemble my network. I will assemble something possible. How will it work? I hope it will work. Who knows? Maybe it will just make kaboom. Strange thing. Why wires always disappear? It's a kind of coast. Okay, I don't need. Nice network. It's from PMMA era. One second, I'll assemble my network and we will see something. I hope. Where is wire number 1? and Y. What do we see? Nice. Nice decaying oscillation. Okay, more optical. 1 second, I just need one resistance box. This one. Yeah, this one. This yeah. Idea. See, pulse generator produces pulses. Each pulse at this moment is 1.5 microsecond in length, and timing between them is 1 millisecond. So at each pulse, capacitor is charged, and when generator goes down, if there would be no diode, it will short circuit the capacitor to its low output resistance. To prevent it, I need it out. So capacitor is charged and left. It's to isolate contour from the low output resistance of generator when it's in off state. Here I need to energy flow only to contour, but not if there will be no diode. When generator goes down, it will take energy back from capacitor.
So it won't charge this coil?
Yeah, it won't charge the coil, energy will go back.
Okay. So it only goes in one direction?
Yeah, I need to ensure that energy flows only from generator to contour. Okay, I can. Yeah, I'm ready. What do we see? Nice oscillations. So here I have a transformer, copper coils with a coupling of 10 millihenries. Now I put the plug off, secondary. Here I have disconnect switch. And we see nice decaying oscillation of resonant contour. Yeah? What will happen when I switch this on? Any idea? When I switch this. Now, plug is off. When I put it in, what will happen?
The frequency change?
At first, it's like, I can draw the schematic, like something like this. Capacitor, coil in parallel. L. With asterisk. Meaning real multiplied by, if, for example, let's assume we have ideal transformer, it will be multiplied by square of winding of transformation radius. I will introduce additional inductance and additional resistance. Take a look. See? Additional losses. How it works? Look, I'm increasing resistance. You see, in case resistance was at primary side, we would solve what? At some moment it will become, a process will become a periodic, yeah? At the moment when resistance reaches double characteristic, double square root from L divided by capacitance, we should see a periodic signal. Nothing here. You see resistance at the secondary part. Higher resistance means lower decay. Because this part plays smaller and smaller role. If I introduce infinite resistance, in case of primary network, we see no oscillation. Here we see an oscillation without any problem. But what will happen with resistance decrease? I'm decreasing resistance. More decrement, more, because I introduce more losses. And in some moment, you see what happened? Again, with the zero resistance, we have short circuit here. But we will have parallel connection of two inductance coils. And it will change what? Frequency. Look. Two coils, 72 kilohertz. One coil, 63. Short circuit inductance decreases magnetic, let's say, capacitance of the network. See? Resonant. At a short circuit, not ideal because coil has its own resistance, but at the secondary side, short circuit means decrease in resonant frequency on the primary side. Increases resistance, we have decay and smaller and smaller role of the secondary part. It's what happens when you have a transient in transformer. As an example, power supply with quasi-resonant characteristic. With no load regime, you will have one resonant characteristic. When you add a load, your quasi-resonant power supply should change its driver of supply should change its frequency to remain quasi-resonant. That's why a feedback coil is mandatory for such kind of supplies. Or I'm speaking PWM type of power supplies. Okay, it will be in future. It's power electronics. You don't have a power electronics course. Okay. Okay, if I have time, I will show the PWM power supply, how it works on modulation. And a difference in quasi-resonant and simpler simple. I have resonant circuit on the primary side. If we divide like this part is resonant, and this part secondary resonant. What do we need for the second order network? Two elements capable to store energy. Coil stores energy, but resistance box, no, only dissipates. I need something like this. I need pair of resonant network output. What will I do? Here, I'm not able to change anything. I'll use different model. I'll use more complicated device. V is answer to the questions V. What do I have here? Show it close to camera. Outer coil, okay, and inner rotating coil. Yeah, it's a coil inside a coil. Why? What's the purpose of this device? Coil inside the coil. Idea, what with rotation changes coupling between coils. Resistance and inductance remains the same. Coils are the same. Nothing changes in coils in, let's say, itself part. But changes part of flux coupled with the inner coil. This allows to change metal inductance without changing other parameters of network. It's a network, in reality, of variable coupling. I can use it as an inductance connecting both coils in series. This will give me ability to change inductance plus minus double metal. Or I can use it as a adjustable coupler. For example, such are used in transmitter to adjust coupling with the antenna part. It's system with variable coupling. It's a heavy object. Yeah. Variable self and metal inductor. It's a system of coil between coils. It's allows linear, with quite good linearity, change metal coupling on my wheel. So it's a system of coupled coil with max of 30 millihenries of coupling. Let's use it. So, with the help of the system, coils are same. This will be variable. This one goes here. 1 second, I'll assemble something. This one goes here. The number one goes here. And. This one goes here. It's a primary part. Here is nice decaying oscillation on the primary part. You can switch this off. 1 second, I need another condenser. More condensers here. Only see where. Here it is, the second air condenser. Ground should go to the ground. This is ground. This will be hot. And school. One moment. This is ground. Ground should go ground. Ground. You go to ground. Okay, here is my network. Nice. Nice. What do we feel now? Generator excites primary coil. And we see nice decaying oscillation, as usual. Secondary one, weakly coupled. And we see, I can change scale. Here they are. Oscillations with the same frequency. Spectrum analyzes all the primary signal. One, frequency of free oscillation of this contour. It's simple. Now, let's take a look what will happen when I increase coupling. See, coupling increase, we have higher amplitude of secondary this one is the first signal, and here is ground, and here is the blue second signal. Let's increase coupling. You see what happened? Secondary network starts influencing primary. I increase coupling. Maybe I can turn to see, to make real visible. See what happens? We coupling one frequency, stronger coupling, and we are seeing, change scale to make it easy. You see what's going on? Secondary influences primary, primary influences secondary, and do you see how many frequencies? 2. When coupling is weak, we have one resonance frequency. With a stronger coupling, second frequency emerges in opposite direction. You see? The second frequency. This is fourth degree network. Such network has not one resonance frequency, but 2. For power engineering, it's interesting because CT network, when earthquake occurred, resonates in this way. We have a strong coupling between damaged phase and health phase. In theory, it can, if phases are very different, we can have free frequency, 6 degrees. But it's real problematic because damaged phase and 2 healthy phases, each with its own double. It doubles. What can I do? One second. I'll show it's in frequency space. The second one just disappeared. See how they influence each other. One moment. I'll bring the amplitude frequency analyzer. Amplitude frequency characteristics analyzed. pair of resonance contours, coil and small capacitor. This is sending, this one will be receiving. I'll get the best possible picture. This is okay. I hope this will work. Can you see characteristic? Yeah, I have chart frequency on the x line, horizontal and transfer, amplitude of transfer function to resonant contour. Small coupling. You see? One, they are adjusted on the same frequency. Can you see? Looks like traditional characteristic of resonant contour. But when coupling is strong enough, what we see? Characteristic tau doubles. See? Make it more visible. Bring another network. This one. Two coils sharing the same magnetic system. One coil, second coil. receiving side. Can you see? I'm introducing additional losses to the one coil. I'm introducing additional losses to the second coil. But you see, well calculated resonance contour, you see, the same thing we saw here. But here we have spectrum of resulting resonance, and this one is a frequency, in frequency space transfer function. You can see two possible frequencies, and there we have two oscillation on two frequencies. Coupled network can produce multiple frequency oscillations. Whose name should we remember first when speak on coupled resonance systems? Black magician of electrical engineering. Who's our candidate? Resonance and coupled networks. What is this? Source, resistance, coil, capacitor ground, spark gap, coupled coil, capacitor. Capacitor, primary coil, secondary coil, and this excess capacitor. White box. Maybe this way better because I can show the spark replacing my battery. P means battery. This one. Yeah, this one goes here. One. Without disturbing anything. So it goes here. This goes here. And more wires for the guard wires. Let's see what happens. Not 100%. Sure, but I think it works. What's this? Smells like ozone. Can you see this card? You can use neon. Neon. Yes, here. Fix it stronger. Nice toy. I don't know, is it possible to get discharge itself? Okay, I need something. A little box itself. Make it more visible. No. It's better in the dark. Nice toy. It's the same thing, pair of cowport resonance contour. This one is primary, excite with discharge. Not a, I use a pulse generator, I don't want to get killed. Classic idea is you use a spark discharge to form a current pulse. And the secondary one oscillates free. Oops. Camera don't like it. Camera is unhappy. Okay, I have time. You need a good toy. Tesla transformer. Definitely a good choice. Okay, bit of theory. Tiny bit of theory. Possible I need to put it in some dark room. So, idea. I have, let's say, pair of resonant. I need to put an energy source somewhere. Coupled by metal inductance. This will be L1, L2. So, the coupling itself can be characterized as coupling factor. I will use S, this S from Latvian side connection. S is a coupling factor. It's a square root from 1, 2, K21, which are voltage transfer factors. In our case, K2 from 1 will be inductance divided by L1 and 1, 2 by L2. Coupling factor is divided by L1, L2. Another, this one what we saw and we see it. Another possible and quite popular model is with capacitive coupling. L1, C1, source, it will be ground. It will have side coupling capacitor. Yeah. And such kind of schematic is quite popular in radio or communication networks. For such network, coupling equals to this side capacitor divided by square root C1 or CS, C2 plus CS. Very popular network. V. In any case, can analyze something, for example, something like this. We will have source. We will have primary impedance. We will have some kind of coupling impedance. It's from Latvian side connection or link, and impedance on the secondary side. So if and will be secondary for that, we can calculate input here, for example, ground. At the point A, we can calculate an input impedance of this network. To analyze network, we need to obtain some characteristic equation. For system of coupling, for example, for this one, where will be the input? Here, at the discharge. To analyze such network, good mathematical approach is to start from input impedance. So at that input, it's at A ground, measured will be 1 plus Z2 divided by plus OR complex. Or input impedance is 1, 1 minus ZS square divided by the secondary one. This is square. And this part is an introduced or transformed resistance or impedance. That's what the secondary I'm introducing active losses where at a secondary impedance. So this part is this, let's say, area secondary transformed or introduced into primary. That's what not the generator here. If I measure at this point, that's what I'll see. Since mutual inductance or mutual capacitance inductance don't have active component, capacitance, in theory we can calculate losses in capacitor veins, but don't bother. We can assume a real part of that has to be 0. And this introduced part or transformed part, the part we will have R transformed plus your X transformed means XS squared divided by secondary R transformed active loss. That's what I introduced with my resistance box. It was X squared transformed divided by square of an absolute value. Remember, I wrote a formula with for ideal transformer with square of transformation ratio. For any case, this is transforming factor. 1 second. I see something wrong. It's S, it's coupling. Sorry. This one is transformation factor for any case, for any coupling. Introduced or transformed part being minus XS squared divided by absolute value squared in reactive from the secondary part changes oscillation frequency. Remember, on short circuit regime we have some change in frequency. This is introduced part of inductance or transformer. Coupling frequencies. When the dog is digging, coupling frequency. To find coupling frequency, we can solve imaginary part of input, impedance 0. This will yield us resonance frequencies. So we will need to solve minus X square S divided by Z square X 0. There is no good solution when the difference of resonance frequency or tuning frequency of contacts are very different. But in small difference, in small difference, we can substitute this term with the square of wave resistance, decrement square plus square of frequency shift. And we will see a easy condition, easy solvable condition of resonant frequency. So we will see one at the zero shift of frequency, one oscillating frequency. This is relative shift from the point of resonance. So one at the point of resonance, and second one being plus minus square root of coupling factor square minus square of decrement. It's so-called coupling frequency. So these frequencies too emerge. They emerge when this term is enforced. We will see two more resonance frequencies in such case. One up, one higher and one lower. Square root 1 plus square root, it's a factor minus square of the decrement. This is 1. And second one will be omega 0 divided by square root 1 minus square root coupling square minus square of decrement. Two frequencies. So the higher coupling, the larger will be difference between these two frequencies. What we saw. And transfer characteristics. What we saw as a green line, transfer characteristic, it's a transfer factor as a function of frequency, will be coupling factor divided by frequency shift in fourth degree plus double square of frequency shift, square of the decrement minus coupling coefficient square plus square of decrement coupling coefficient square. Case analytics for transfer function. As a function of frequency. This is no need. So, what the conclusion? Can we make any conclusion? Any conclusion? First, Tesla coils are good toys, and second, when we have coupled resonance system, we will have multiple resonance frequencies, not one, not single. And distance between these resonance frequencies depends on, let's say, coupling strength relative to the energy capacity of the resonant contact itself. The stronger coupling, the bigger will be difference or distance between these paired resonance frequencies. They are paired, amplitudes are not amplitudes are different, but distance between resonance frequency is symmetric relative to the original, or let's say natural resonance frequency of the weakly coupled system. So in my case, it's observed in case of fault in city network. I don't know, some power driving system, you see coupling between winding of electrical machines or something like this, or I don't know, power supplies. There are a lot coupled networks around us. Okay, I think it's enough for today, yeah? So I can